Alright, so calculus is made up of two branches, differentiation and integration. Differentiation allows us to work out things like the gradient or rates of change problems, and integration allows us to work out areas and volume. Both differentiation and integration are intimately related, and I'll show you how later on. And it's probably the most important tool in maths. We wouldn't have any practical science. Man would not land on the moon. We wouldn't have modern science, modern engineering, technology as we know it if we didn't have calculus, let alone things like quantum mechanics and string theory and what have you. Okay? But just the basic idea, basic application of math to the real world, we wouldn't have much if we didn't have this branch. Let's begin by looking at differentiation. In terms of differentiation, let's just look at what's going to happen. Say I've got a cubic. Okay. Let's make that plus 2. And let me add another one in here, x minus 3. Okay, so say I've got a cubic that looks something like this. Okay, so say I've got that. There's my cubic. I then take a point on this cubic. Let me put a point there. And I can actually work out the tangent of the curve at that point. So as I move this point around, it tells me the tangent. I could actually go one step further, and if I click on slope, that triangle tells me is a visual representation of the gradient. So over here the gradient is 0, over here it's positive, and it increasingly becomes positive. Over here it's negative, here it's 0 again, and then here it's positive. Is that okay? Right, so that's GCSE stuff. Yeah, there's a gradient of the curve. But what if we were to plot the gradient? So as I move this around, for every x value, I record the gradient. Let me see if I can actually put that in a spreadsheet and put something like x and the gradient at these points. I'm not sure if this will work. That's 29. But what I'll try and do is record this on a spreadsheet. Okay, and I'll also trace it. Let's see if this works. Fingers crossed. I'll move this down. It's actually tracing that, which is fine. Okay, it's gone all the way down. Okay. Let's see what it's got. So on the one hand, I've got x. On the other hand, I've got y. We don't really want that. I think at this point here, the gradient, so that just gives me my x and y coordinates rather than, so it's not quite what we want. Let's change that. Let's put the trace off and clear all traces, close. But what I'm going to do is, actually what I could do is click on here and record the slope. That's what we want. We want the slope on the spreadsheet. Okay, start at row 1. So say we did this. Here we've got, this is better. Okay, if I take this now, okay, and took this all the way down, okay, then this is what I've got now. So at each point I've got 3 values: x, the y part, and then the actual gradient. And if I was to plot the gradient against the x values, so at every single point, if I was to figure out what the gradient is, then this is what I'll get. That blue line there. The blue line there is what we'll get. Let's double check that. Okay. Let me just turn the recording off. Let's put that aside. Let me turn that off. Here, let's double check that. Here the gradient is 0, and therefore this crosses at 0. Okay. here the gradient is negative, and therefore the y value goes below the x-axis. Okay, here it's 0, and therefore it crosses at 0. Here it's positive, and therefore it's positive here as well. Okay, so if I was to plot the gradient function of a cubic, we get a quadratic. Okay. However, if I was to change this cubic into a quadratic, who can guess what I'll get for the gradient function? A straight line. If I now change my functions around a bit, so now this time I've got my quadratic, and I'll work out the gradient at every single point, and I plot that gradient against the x values, I actually get a straight line. Let's check, because here the gradient is 0, so it'll cross here at 0. Then it gets increasingly positive, it just goes up, whereas on the other side of this it was just negative, and therefore it just goes below the x-axis. Okay? Differentiation allows us to work out the gradient function. It allows us to work out the gradient of our original function at any point we want. Okay? In terms of, so what I'm going to do is start by showing you the formula. We'll practice, we'll see how to apply it, and in terms of understanding where the formula comes from, that we'll do next week. That involves what we'll use Newtonian ideas of first principles and be able to come out with the actual formula for differentiation using those first principles next week. I don't think it's a good way to start off differentiation. It can be quite off-putting if it doesn't click. But it's better just to say, how does this work? Okay, how do I apply it? And then we look at why it works. Okay, so let's look at something like this. Say I've got a function, and the function is 3x squared plus 2x plus 1. Okay? My gradient function, the gradient function, which is the gradient of this curve at any point, can be written in two different ways. I can either write f prime x, or I can write this as dy over dx. Okay. Given that if I use the y notation, then use dy over dx. If you've been given the fx notation, then use f prime x. And the way it works is simply as follows. You will get 6x plus 2. And we can check that using GeoGebra. So 3x squared plus 2x. So on here, if I do 3x squared, 3x all squared, so 3x squared plus 2x plus 1. Okay. When I differentiate it, as you can see here, you get 6x plus 2. Happy? Okay. Let me just bring this down. Let's just turn this off. There's my gradient. Okay, I can bring that up there. So let's take...
So what does that mean, f?
That's the gradient. The gradient of fx, yeah, is f prime x.
We've got calculator in the system.
Yeah. And that gives you 6x plus 2. Let's now change our fx, and let's make this 2x cubed plus 2x, or 4x plus 5. Look what happens now. Now we get 6x squared plus 4. Let's write that down. So if you've got, I'll write it down over here. If you've got fx equals 2x cubed plus 4x plus 5, then the gradient f prime x is 6x squared plus 4. Can anyone see a relationship between fx, f prime x? Go on.
I'm just trying to work it out. Is it, do you add the two x cubed and squared with the 4x to get 6x, and then use the value of x to get the number?
Well, yeah, maybe, but what I'm trying to ask is, how do I go from fx to f prime x without using the software package at the moment? Yes.
You get the power and you multiply it by what's that called,
The coefficient.
A minus 1 from the power.
And then minus 1. So you do 2 times 3, which is 6.
Yeah.
Take away 1. Was anyone else going to suggest anything? Alright, so with the 4, what's the power here? 1. So you do 4 times 1, take away the power, that will give you x to the 0. So over here, this is really x to the 0, isn't it? What about here? What happens to that 5? It disappears, because in essence, this is x to the 0 in a way. And when you bring the power down, you just get 5 times 0. Anything times 0 is just 0. And so that disappears. Let's see if that works here. You bring the power down. 2 times 3 is 6. That works. 2 take away 1, which just gives us a power of 1. The 2x just becomes the 2. So x to the power 1. Guys, excuse me. Bring the power down. So 2 times 1. Take 1 away from the power. So that becomes x to the 0. I can write that in here if you want. This is x to the 0. So 0 times anything, that just becomes 0. So that any constants just disappear. Let's just test that one more time. Well, in fact, let's just write out the rule using algebra. If I've got fx equals ax to the power n plus c, then f prime x is n times ax to the power n minus 1, and the c just becomes 0. I'll write this using the y notation. Y equals axn plus 1 plus c. Okay. Then it follows dy over dx, which is my gradient, equals n times ax to n minus 1. So that is written using 2 different notations.
So could you go through the second example again?
Fx equals 2x cubed?
Yeah.
Yeah. Just give me a second. So with fx equals 2x cubed, we've got 2 times 3, which is 6. 3 take away 1, which is 2. You've got 4x to the power 1. The power comes down, so you've got 4 times 1. You take 1 away from the power, so you get x to the 0. Any constants just disappear. The reason why they disappear, you can think of this as 5 times x to the 0. The x to the 0 is simply 1. When the power comes down, anything times 0 is just simply 0. Yes?
So you know the second line in the box, what does that mean?
This one,
Yeah, the whole line.
same thing as the top line.
Sir, second example one more time, please.
Just a minute. Guys, with this, you've got different, depending on, when you're treating a function, you can differentiate a function. They've given us this equation in terms of y. So y equals 2x cubed, take away 5x squared plus 4. Say you want to find the gradient at any point on this curve. So the gradient of y is written as dy over dx, and you bring the power down, so you've got 3 times 2 times x, you take 1 away from the power, minus 5 times 2 times x, you take 1 away from the power, and any constants just become 0. That's it. That's all you need to know.
But why does any constant become zero?
The reason why they become 0 will be better understood when we do integration, and you understand why you have a constant of integration and what that means. But for the moment, let me just say another way to understand this constant is to say this is x to the power of 0. And so when you bring the power down, okay, like the rule tells us to, then 0 times anything is just going to be 0. And so you end up with 0. That's one temporary explanation. But in terms of graphically understanding what's going on, we'll go over this when we do integration. Yes? Yeah, this is saying you bring the power down. Look at the rule over here. The rule here is you bring the power down, you take 1 away from the power. So the 3 comes down, take 1 away from the 3. The 2 comes down, take 1 away from the 2. And that's it.
Anything to the power of 0 is 1, isn't it?
Yeah.
Anything from 0 is the plus.
Let's look at a couple of more cases that you should note down. Let's say we have to say we've got an expression like this: y equals 3x squared take away 4x to the power of 4 divided by 2x. And the question is, we should differentiate y. The way we will do this is firstly put y down in what we call index form, where you don't want it as one fraction over another. You want it in simplified form. So you've got 3x squared over 2x minus 4x to the power of 4 divided by 2x. We can then simplify this down. So 3 over 2 is simply 3 divided by 2. X squared over x gives us 4 divided by 2. X to the power of 4 divided by x. Now we can say dy over dx, the first term, this is to the power 1, don't forget. So what's that? What's going to happen? 3 over 2, I'm just going to write this out for now, times 1 times x to the 0. So you bring the power down, take 1 away from the power. Minus, what happens to the next one? 2 times 3 times x to the power of 2. I'm going to write down 3, take away 1 for now, just to show the method, just to show what I'm actually doing. And this becomes 3 over 2, x to the 0 is just 1, minus 6x squared. Do you see how that works? Alright. Alright, let's look at something like this. We have to differentiate this curve y, and then we have to use our answer to find the gradient of the curve at this point, where x equals 2. And then we have to find the coordinates of the points where the gradient is 0. So let's do this step by step. Hands up if you'd like to have a go. Hands up if you'd like me to go do it. 2 people, 3 people. Alright, let's do it together. If you expand this out, x squared times x, what does that give you, Sammy? X squared times x. X cubed. We've then got x times 1 gives us what? Samina. X times 1. Okay, x squared times minus 2, Sabiha. Minus 2x squared. Minus 2 times 1, Isa. Minus 2. So we've got that. We want to find the derivative. Okay, the word derivative means to differentiate. Okay, the differential, the gradient function, in other words. So dy over dx equals, Zayn, what would you get for the first one? So bring the power down, take 1 away from the power.
So the x
bring the power down, so that x cubed, thank you, stop there. Okay, the next one, Hendrik, what would the next one be? X, you bring the power down, take 1 away from the power. Bring the power down, so what's the power here? 1. You bring that down, take 1 away from the power, x to the naught equals x to the naught, 1, thank you. Next term, James.
So it'd be minus 4x.
Excellent. The last term, Jan. 0. Excellent. So then we worked out the gradient. The first part's been done now. The second part, find the gradient when we're at this point, 2, 0. So at 2, 0, what does x equal to? 2. Therefore, dy of dx, the gradient, equals 3 times 2 squared plus 1 take away 4 times 2. 2 squared is 4. 4 times 3 is 12. 12 plus 1 take away 8. That gives us 5. And so the gradient at that point is 5. And while you're copying this down, I'll just quickly load up GeoGebra on the other screen and just put this equation in. X cubed plus x minus 2x squared, and then take away 2. And so here we've got, I've just plotted this function. Here's a function, x cubed plus 2x, take away 2. If I move this down to x equals 2, as you can see here, the gradient is indeed 5. Yeah, so when x equals 2, the gradient. So if I plot the gradient function, when x equals 2, on the gradient function here, oops, the gradient function, let me put that there. Okay, when I move this down, I should, when x, here it is, when x equals 2, y equals 5. Okay. Last but not least, so we know what we've done so far. We take a function, we can differentiate it to find the gradient function, i.e. we can work out the gradient, and then given a coordinate, given an x value, we can work out the gradient at any point on that curve. Now it says find the coordinates of the points where the gradient is 0. So how should we do that? Any suggestions? Yes?
You just put it, you replace y with 0. So it's
Play
0 equals
y with 0?
Oh no, the gradient.
The gradient. So dy with dx is my gradient, and we set this to 0. In other words, 3x squared take away 4x take away 1 equals 0. If we were to factorize this, we'll get 3x take away 1 and x take away 1 equals 0. It should be minus 1. No. 3x squared. Oh, so at the top. Yeah, so here it's plus 1 and a minus 1. Thank you. Now, the only way for this to be 0, nicer, guys, for this to be 0, either one of these brackets or both of them need to be 0. And so therefore, either 3x minus 1 equals 0, or x minus 1 equals 0, and so x equals 1, or x equals a third. Have we answered the question?
No.
Why not? Because it says coordinates of the points. Where should we substitute to find the y values? In the original cubic. So if we take this down, here's my original cubic. And if we substitute in the y values, we should get y equals minus 50 over 27 and y equals minus 2. Now it's always good to write this as a coordinate. So 1 minus 2 and a third minus 50 over 27.